Hi, we're going to graph y equals secant x, cosecant x, and their transformations. And you're going to find that this is pretty easy, I think. So let's first look at y equals secant x. I want you to remember that y equals secant x is the same as saying y equals 1 over cosine x. And if we look at it as if it's a rational function, then it would be pretty easy to come up with some vertical asymptotes. And remember, you're going to get the vertical asymptotes if the bottom goes to 0. So if you go around the unit circle, do you recognize that cosine x is going to equal 0 at any multiple of pi over 2? So 1 and negative 1 pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, etc. So I'm using kind of a slang shortcut for my answer here. Now, the other thing I want you to recognize is that if cosine x equals 1, then secant x, the reciprocal, would equal 1 as well. Or if cosine x equals negative 1, then secant x is going to also equal negative 1, because when you flip negative 1, 1 over negative 1 is just still negative 1. So let's focus our energies for just a minute on graphing y equals cosine x. So I'm scaling my x-axis like you're supposed to do. And I'm going to go ahead and draw in my dotted guidelines because I think they're really helpful. And it'll keep my graph really nice and neat. And now I am going to go ahead and proceed with graphing y equals cosine x. And at this point, this graph should be really second nature to you. And let me draw the cosine wave that attaches those points to one another. All right, so now in red, I need to go ahead and start graphing y equals cosine x. Well, I know that I'm going to have vertical asymptotes when cosine x equals 0 or through the x equals pi over 2's. So I'll tell you what I'm going to do. I'm going to go ahead and draw those vertical asymptotes. I think I will draw them, whereas you might dot them. I think I'm just going to draw them in a different color. So I'm going to use kind of a light pink to draw mine. And I know I've got a vertical asymptote through pi over 2. And through 3 pi over 2, and through 5 pi over 2, 7 pi over 2, 9 pi over 2, and so forth and so on. So now I'm doing the exact same thing, but I'm doing on the negative side. Hey, do you recognize that so I don't have to get so hung up on the coordinates where I'm crossing through my vertical asymptotes? But look, I'll do this in dark blue so you can see me handling it. Look, I've got a root on the cosine wave. I wind up getting a peak vertical asymptote that goes with the secant graph. I have a root on the cosine wave. I have a pink vertical asymptote for the secant graph. And look, I repeat that pattern throughout. So what I'm suggesting is it's not necessary to name the coordinates of all the vertical asymptotes if you just know that wherever the cosine graph crosses through its axis, the middle points, so to speak, then you know that the secant graph is going to have asymptotes. And we'll say the same thing is true when you're graphing sine and cosecant on the same coordinate plane. So, back to business. I want to use the information that says whenever cosine x equals 1, secant x equals 1. So what's that look like? Well, it means that this max on the cosine wave, that point will also be on the secant graph. And at this min, right here at x equals pi on the cosine wave, that point's also going to be on the secant graph. And I could go on and on doing that. And so what you're going to notice is everywhere my cosine graph goes through its max or min, then I'm going to attach my secant graph to those points. Now, what do I mean by attach my secant graph? I'm going to work from right to left. Look here at this point, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It looks like I have... I was actually counting. Sorry about that for a minute. It looks like that I have a place on the graph between two vertical asymptotes, and because the cosine graph is below the x-axis, that means cosine's negative, and whenever cosine is negative, secant must also be negative. So I've got to figure out how to attach my graph to this red minimum and then make it be attracted toward this left and this right vertical asymptote. It's got to stay below the x-axis because it must be negative. Well, the only way to do that, you probably remember from graphing rational functions, is to sort of make it look like it's a parabola shape. Well, the same would be true here at this red maximum. My graph must be positive because if cosine's positive, meaning cosine's above the x-axis, secant must be positive and be above the x-axis as well. So that means the graph can't go down because it would cross the x-axis. I've got to make it go up so it won't cross the x-axis. So once I get that pattern, then all I have to do is go to every max and min on the cosine graph and attach one of these parabola-like shapes, and the red parabola-like shapes as a whole form the secant graph. So notice y equals secant x has no x-intercepts, no roots, okay? I also notice that to complete a period of y equals secant x, then I have to have both an upside down and a right side up parabola. So take a look. I'm going to just kind of thicken this so you can see me drawing it. So if I need an upside down parabola-like shape plus a upside down, right side up and upside down parabola-like shape before I begin to repeat the secant graph, then that means I need to go from this leftmost vertical asymptote to this rightmost vertical asymptote, and that would create one period. Well, I notice that if I go from negative pi over 2 all the way to positive 3 pi over 2, from negative 1 to 3 would be 4 pi over 2 units wide. Oh, so what am I telling you? I'm telling you that the period of the secant graph is y equals 2 pi, because 4 pi over 2 reduces. So that's what you need to know. So here's what I'm thinking. I'm thinking if I ask you to graph y equals cosecant x, you could do it pretty quickly. Are you with me that what I really want to focus on is y equals sine x? So let's do that. Scale your x-axis like you know you should. Graph your sine wave. Or let's try something a little bit different that some people prefer. So you'll have an example done both ways. Some people prefer to graph the sine wave in, like I did on the previous cosine graph. Some people prefer to just plot the points that would be on this sine wave. Either is fine with me. Whichever one makes more sense to you is A-okay where I'm concerned. Now, if I repeat the same idea as I did a little while ago, the idea was since y equals cosecant x equals 1 over sine x, then the vertical asymptotes will occur when sine x equals 0. And if sine x is equal to 0, I'm looking at the x-intercepts of the sine graph, or the middle points on the sine graph. So all these middle points right here on the sine wave, the ones that are currently on the x-axis, it's through those points that I need to create some vertical asymptotes. So that's what I'm going to do now, is draw my vertical asymptotes through. I like having this handy dandy line tool. I bet if you all could just quickly push a button on your notebooks that would force you to have straight lines, you'd probably like that. Instead, you might have to get out the old ruler or driver's license or something to make them nice and straight. So now it's time for me to graph the cosecant graph. So I'm going to use the idea that if sine is 1, cosecant must also be 1. If sine would be positive in this range, then cosecant must also be positive. So in other words, my right side up parabola-like shapes attach to the maxes of the sine wave, and the upside down parabola-like shapes attach to the mins of the sine wave. Well, that's no big deal. That's actually pretty easy, isn't it? So most people find that this is one of the nicest days in trig ever because it's pretty quick. Not real hard to understand, and I think you're going to do a great job on your homework. In fact, I'm thinking you're going to get it done in class, which is my hope. All right, so I want to reiterate, on y equals secant or cosecant x, there are no x-intercepts. You will have vertical asymptotes wherever sine is 0. So that's at x equals 0 and x equals any multiple of pi. So plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, etc. Now also consider this, that just so when you see wording like this, you're not thrown by it. That if you have a max point on your sine wave, like here, see where I'm pointing? That's a max point on my sine wave. That's actually a minimum value on my cosecant graph. And by the way, the period for cosecant, just like it is for secant, is 2 pi. So just as a matter of vocabulary, if someone asks you where the minimum points of the cosecant graph are, you're actually looking for the maximum points of the sine wave and vice versa. So let's take a look at graphing a crazy transformation. All right, well, I'm just going to tell you, I don't think you're going to have a hard time with this. What I'm going to do is I'm going to focus all my efforts on graphing y equals negative 5 sine of 2x plus pi over 4 plus 5. That means really my effort is focused on just doing a review problem like we did the first few days of this chapter. So here are the things I can see very quickly. The axis of my graph is going to be at 5. The amplitude of my graph is 5. If I go from a y coordinate of 5, and I'm going to go ahead real quick, if you all will give me a second, I want to make sure I'm demonstrating what I'm saying. Well, that was not exactly what I meant to do. There, that's better. If if I go from my axis, which is at y equals 5, and I drop down the amp, my lows are going to be at 0. And if I go from 5s up the amp, my highs are going to be at 10. So that's why I really just need guidelines at 0, 5, and 10. So now the y stuff for my sine wave is determined. Not a big deal. So at this point, the next thing I need to do is figure out what's going on the x-axis. What's happening with my period and that sort of thing on the x-axis. So I'm going to go into the 2x plus pi over 4 equals 0. 2x plus pi over 4 equals pi over 2. 2x plus pi over 4 equals pi. So my general x stuff, and by now I hope you're getting really pretty quick at doing this. So this would give me 2x equals negative pi over 4. X equals negative pi over 8. Pi over 2 minus pi over 4 is pi over 4 again. 90 minus 45 is 45. So x equals positive pi over 8. Here I've got 4 pi minus 1 pi is 3 pi over 4. X equals 3 pi over 8. So it looks like all my big stuff is going to happen on multiples of pi over 8s. Let's see here on this one. I'm going to say that 3 pi over 2 is the same thing as 6 pi over 4. Minus 1 pi over 4 is 5 pi over 4. So if I'm going from negative 1 to 1 to 3 to 5 pi over 8, this has got to be 7 pi over 8. I've got to follow suit. Well, that means when I'm scaling my x-axis, I need to say 1 pi over 8. This tick mark would be 2 pi over 8, 3 pi over 8. This tick mark would be 4 pi over 8, 5 pi over 8, 6 pi over 8, 7 pi over 8. So there's got to be tick marks in between them, guys. But I'm personally only going to label the odd ones, because the odd ones are where I'm going to make marks on my sine wave. You only have to label any 4 to the right of the origin. But I'm going to go ahead so I don't have to keep counting backward, and I'm going to label all the ones where I need to make marks. And you don't have to do that. But it seems just as easy to me to do that. So I know that I'm going to start my sine wave, which is negative, at negative pi over 8. And I know that sine starts on the axis of its graph. At pi over 8, since it's a negative sine wave, I need to go down. At 3 pi over 8, I need to come back to my axis. At 5 pi over 8, I need to go up to my max. And at 7 pi over 8, I need to come back down to my axis. So I'm going to kind of split the difference with you. I'm not going to draw the whole sine wave. I'm going to draw part of it, and after that, I'm just going to plot the points. Does that look like the correct upside down sine wave to you? Back in action, guys. I turned off the microphone there for a minute so you wouldn't hear all the announcements. I hope that we're back on track correctly. So if that looks like the correct negative sine wave to you, then the next thing I'm going to do is simply extend the graph to the left and right to make it look periodic. All right, I just wanted to make sure that I hadn't skipped anything there. You saw me kind of air tracing it. So it's time. Without overthinking it, I'm going to switch to my pink pen. You're still just doing dotted lines, or you could do real light solid lines if you wanted to. And I notice that negative 5 pi over 8 is a middle point on my sine wave. Negative pi over 8 is a middle point on my sine wave. 3 pi over 8, same thing. So when I say a middle point, I'm talking about the points on the sine wave that go through the axis of the graph. And then in this case, the axis of the graph is at 5. So any point on the sine wave whose y-coordinate's 5. Once I have those plotted, all I have to do is make sure that I've left exposed the mins of the sine wave. So there's a min. Take it toward the vertical asymptote. There's a max. Take it toward both vertical asymptotes. Min, max. So if you'll draw vertical asymptotes through the middle points and don't touch the mins and maxes of the sine or cosine wave, then those will leave the highs and lows of the sine and cosine wave for you to attach your parabola-like shapes, and you are done. So we'll go to the board tomorrow to work on this topic and make sure you can do 1 or 2 examples at the board. Well, just like we did with y equals tangent x and y equals cotangent x, let's solve a couple of equations graphically. So what I want you to do is graph y equals secant x in red and y equals 2 in blue. This is the same thing we did the other day with the tangent graph when we solved an equation in terms of tangent. So I am going to scale from negative 2 pi to positive 2 pi. And so, of course, I've got pi over 2, pi, 3 pi over 2, ditto on the other side. I've got 1 and negative 1. I'll go ahead and put 2 and negative 2 on the graph. Those don't have to be perfect. You'll still be able to see what's going on. So I'm going to graph my points that should go on the cosine wave. So cosine would be these red points. And yes, I'm going to graph secant. But remember, you always start with cosine and then go to secant. And I am going to dot my vertical asymptotes in. So this time I'm not using my pretty line tool, so you can basically see what you would be doing. I'm going to attach the up and the down parabola-like shapes. Now, I need to graph y equals 2. Y equals 2, of course, is a horizontal line. And same thing, I'm just going to extend it from negative 2 pi to positive 2 pi. So when I look at this, I notice that I have 1, 2, 3, 4 points where the blue horizontal line intersects the red secant graph. So now I need to figure out, well, what are those 4 points? Well, I know if you look at the 30, 60, 90 triangle, and you do secant of 60, you'll see that hypotenuse over adjacent is 2 over 1. So I'm telling you that the reference angle is 60 degrees or pi over 3. Since I'm graphing, I'll be answering in radians. Well, I'm going a little bit out of order. I know that I need 4 solutions. I'll go ahead and make blanks so you can see where I am in the problem. I see that the third solution here falls, if you come down to where it would be on the x-axis, that's between 0 and pi over 2. Well, between 0 and pi over 2 would be this solution, which is just pi over 3. And I'm going to put that in order from left to right as my third solution. Well, guys, this point I can see is just the negative reflection of that. So my second point is negative pi over 3. I don't have to think as hard there, which is kind of nice. Now look at my fourth point. My fourth point, if you drop down and mark it where it would be on the x-axis, I can see that it falls between 3 pi over 2 and 2 pi. So 3 pi over 2 and 2 pi means the point would be there on the unit circle. Well, I know that that's 5 pi over 3 that falls in the cosine quadrant. Well, look, the first point that you get to in order left to right, you're also looking at it falling between 3 pi over 2 and 2 pi, but on the negative side. So it's negative 5 pi over 3. And remember, since secant is even like cosine is even, that's why you're getting the plus and minuses of the same numbers. So that's how you're going to solve those graphically, just like you did with y equals tangent x and y equals cotangent x on last night's assignment. We are going to stop with the first part of the lesson, then we'll pick up with the second part of the lesson, which is just a few examples over the damped trig functions.